Hey everyone, I hope you all are safe and doing good. So, till now we have seen arrays and array list. Now, from this lecture, we are going to start linked list. So, this would be the basic lecture. In this lecture, we will see what is linked list and why basically we need linked list. How linked lists are different from arrays and array list. Because all these are arrays are data structure. Linked list is also a data structure. So, why we need linked list data structure? What are some drawbacks in arrays and array list that is not there in linked list? And what are some other drawbacks in linked list? Because everyone is having its own pros and cons, right? And then we'll see types of linked list and some basic terms we use while discussing linked list, like node and all, how to create a node, structure of a node, and this thing. And then memory representation of linked list, that also I'll show you the working basically, right? So, first thing, we see what are some drawbacks in arrays. We know everybody know about arrays. Array is a linear data structure. Linear means basically we have classification of data structure to the data structure are classified in two types, linear and non-linear. We have discussed this thing. Linear means data is in a linear fashion, sequential fashion, something like this. Non-linear data is not a linear fashion like tree and graph. These are non-linear data structure. Arrays, linked list, these are linear data structure. Got it? Now, okay, it's a linear data structure. Now we know that there are some drawbacks in arrays. Everybody can say that yeah, arrays are of fixed size. Very first, if I ask like what are drawbacks of arrays, yeah, definitely everybody can tell these are of fixed size. Means while creating, at the time of creation only, you have to give the size of the array something like this. If I give the size here something like this, int and 10, so I can store only 10 elements in this array, 10 integer type elements. And if you want to store 11, then manually you have to create a new array of size 11 or 15, whatever you want, and then copy all the elements of this array to that array. And this is how things works. So manually you have to do resizing, and this would be tedious task. Obviously, it's costly in the sense, in the terms of CPU computation and those cycles, right? You have to do some extra work. Or at first itself, you declare array of size, suppose 100, maximum size. In this case, there is wastage of memory, because if suppose I'll store only 15 elements, but I have reserved the space for 100 elements. So for the remaining memories are wastage because I'm not using it. So there are few drawbacks of array. Fixed size, overflow is also there in arrays. If array is of 10 elements, you can add, and if you want to add another elements, then it will cause overflow errors and you have to do resizing. So it's costly in that case. Memory wastage is also there. Okay. That's why. Okay. Now you will say that solution is we can use array list. Yes, because array lists are dynamic in size. I have discussed in the previous lecture. Okay. So solution is you can use array list. Okay, fine. We have array list also. And in array, one thing, elements are stored in contiguous memory locations. Right? One after another, something like this. One after another. We know this thing. So problems in arrays are this. Solution is array list. Dynamic resizing. You have to give any a size in array list. Like if suppose I write here something like this, array list and of integer type, integer, and name is suppose arr, or let's take list is equal to new and array list here. So you don't have to give here the size, right? You don't have to give here the size of the list. Initial capacity by default is, we know here it's 10. You can add elements. If you want to add in a 11th element, you don't have to do any manual resizing. Automatically the capacity would be increased for this array list. How? It's almost 50%, increases by 50%. Like whatever the old capacity, that was 10, plus that old capacity divided by 2 plus 5. So new capacity would be 15. If suppose you want to add 16th element, so the new capacity would be 15 plus 15 divided by 2. That is 15 plus 7. It's 7.5. So integer we will take. So it's 2. So it will be 22 elements. So, and the old array would be copied to the new array, and that's it. But all these things are happening internally. We don't know. We don't have to do manually this thing, right? So that's why we say that it's dynamic sizing. We don't have to give the size, but still these things are happening. Na? So it's like here we have automatic capacity management, but still these things are happening internally. So internally this is using an array itself, and it is going to call that. I have shown you that copy of method to copy the elements and all. So internally the things are happening. So still it's taking time, right? It's not like that we don't have to do this kind of thing, resizing and all. And no, these things are happening. Although manual resizing is not required, it is automatically done, right? Right. So that is one case here. So this thing is simplified. Still, to somewhat memory wastage is there, we can say, because when resizing is done, suppose I want to add 16th element, so the capacity would be 22. And suppose I have used only, I have done only 16 element itself. So the remaining capacity, the remaining elements, the remaining memory would be wastage of memory, but not that much. Okay, not that much like we have in array. Suppose at first itself, declare the maximum size array 100. But still, to somewhat there is memory overhead as well as somewhat memory, you can say, wastage in array list as well. Plus operations we perform. Like, okay, one thing is, in array and array list we are having index. So we can directly access any element. Direct access is possible. That is a good thing, right? But insertion and deletion takes time. Shifting is required, we know. If I want to add, there is an array. If I want to add this element here or an array list, then I have to shift all the elements one by one to the right side. Then I can add itself, right? If I want to add an element here, if the array is full, in that case also, first resizing is to be done. Take a new array and then copy the element this, and then we can add. So that also would be order of n kind of thing. It's a tedious process. So basically insertion and deletion takes order of n time complexity here. Shifting is done. Yeah, if you want to delete an element from the last, you can directly delete in order of 1 time complexity. We don't need any shifting. But if you want to delete this element, then shifting is required. You have to shift all the elements one place to the left, right? Both in array and array list. So these operations are like costly, having time complexity order of n in worst case, right? So whenever you have some data and you require frequently insertion and deletion in that data during the execution and all. So it's not at all a like good practice to use arrays and array list. So then what we can use? Then here a next data structure comes into picture, that is linked list. As the name suggests, linked list. It's itself a list which is linked together. Okay, let me just discuss this thing. I guess this is clear to you. Drawbacks are clear to you. That's why we are using array list. Now we will see what are advantages of using array list. These are limitations of array list. Deletion overhead, contiguous memory. Still contiguous memories are there in this. Insertion inefficiency and memory reallocation is still required. Resizing is still required. Right? So these are limitations of array list also. Now let's see. One more drawback is what? These are in contiguous memory. Right? So let's see. Now linked list comes into picture. Now what is a linked list? It's a linear data structure itself, right? Here also we store the elements. We store the elements. It's a list itself, but in non-contiguous memory locations. It's not like that you have to store. Suppose in a list, in my list, I'm having 3, 10, 5, 6. So in heap, obviously, we create an arrays are also like objects. So in heap, they are created. Linked list are also be created in heap, and reference variables are be stored in stack area. So we create here. Suppose here I'm having 3. We created a in linked list. We call these things node. Why node? I'll discuss this thing also. 3. It's not like that 10 should be here itself. Contiguous memory location. No, 10 can be anywhere. 5 can be anywhere. 6 can be anywhere in this memory. First thing, linear data structure. It is a linear data structure, and elements are stored in known contiguous memory locations. Right? I want to add another node. Just create another node, and that's it. Suppose here 15. So 15. But now the problem is, I say that it is linear data structure. So how I access these elements, right? Like at first I am having three. So suppose I am having here, linked list is something like this. I'm having a pointer head, which is pointing to the first element, first node of the linked list, right? Only this thing we know. Now, have to go to the next element, that is 10. How I go to the next element? I don't know the address of this, right? So it's not like that we can store only 3 here. In linked list, you have to store something else. The address of the next node, the next data. Then only we can go to that data, because these are not contiguous. It's not like that in arrays I have address of this. So I can surely say that the next element I'll get in the next location itself. I don't need any address. So address can be directly computed. Next element would be here, next element would be here, something like this, right? But here we cannot say this thing. You have to store the address, right? So data plus address of the next node. Here also after 10 we are having 5. So create a node 5, 10 store and address of 5, something like this. Reference of next node, reference of next node. Then 6. Okay, 6 is here. This 5. So we create here 5. This will have address of this 6 pointing to this. Now after 6 we are having 7. So let me just do something like this here. Now the 6 is having address of 15. Now I know where is the first node. That is, we will be having head pointer or first pointer. We generally call it head of the linked list. This is the head of the linked list. Now, if you know where is the head, I can easily access, traverse all the elements in that linked list, because I know my head is having the address of next element. So I can go here. Now this is having reference or address of the next element, next node. I can go here. I can go here. I can go here. Now, what this last node will have address here. There is suppose no next element, so it will store null, right? So this is linked list, basically how this is stored. So it is a linear data structure, because we cannot directly, so like tree or any kind of thing, we can go sequentially from this to 10, then 5, then 6, then 15, something like this. Linear fashion. Data is in linear fashion itself. Linear doesn't mean that the data have to be in contiguous memory locations. No, it can be scattered in the memory, but still in linear fashion. Linear fashion means I can go from there to there, next, next, next. There are no branches like in tree. We are having root and some branches, then some again branches and something like this. No, right? Okay. So it's a linear data structure. Elements are stored in separate nodes. Nodes. Now, why we call these nodes? Because we are not just storing the data like tree, like in arrays we store the data, tree itself. Here we are storing the data as well as the reference to the next node. So complete this thing is known as, we call it node, not simple element or data. So a node is having two parts. I hope now you have the idea. If I say node is having two parts, one is data part and one is next. We can call it next. So or we can call it next pointer, or we can call it data part and a reference to the next node. So two things are there within a node. This is basic structure of a node. Data and next pointer. Yes. So somewhere in heap we are having. So head we are having in stack, and this head is like referring to this. Although we are having tail as well. Why we need tail? That also is it. Tail, as the name suggests, the last element. One pointer is tail. One, you can say that reference variable, no pointer concept are there in Java. So basically we don't call pointer. We call it a reference variable. It's a node which is pointing to tail, the last node of the list. Head is pointing the first node of the list, right? See why we need tail. Basically, let me just briefly tell you. If I want to add here, insert uh, element, a node in the list at the last, here after this 15, and I don't have tail, So basically in list we are having head itself, only one. I know where is the first node. So you have to traverse first, you have to go to 10, then 5, then 6, then 15, and then I can insert the next node. Yes, you just have to update the pointer, that also you'll see. In that case you have to traverse the complete list. So it's order of n. But if you have tail pointer, so we know where is the last node. So we can after this directly add next node. Rather than traversing the complete thing, it's order of 1. That's why tail is required. Tail is like, yes, it's you can say useful pointer, right? I guess now you know what is head and tail, right? Node structure is also there. So each node contains data and a reference to the next node. So what is structure of node? Data field, it holds the actual value. This is the data field. Next field, reference to the next node. This is next field. And final node is containing, it's like points to null itself. So last node is null. Got it? Okay. So just I have just shown you what is how the memory is to be represented. Like stack, we are having, it contains the reference variables. Reference variables, like we are having head, that is a reference variable. This is having in that stack, and in heap actual nodes are there, right? Pointing to the linked list objects. Head reference variable stores the address of the first node. In heap memory, actually we are having the data stores actual node object. Nodes are scattered throughout the heap memory, not contiguous, right? Now, it's not mandatory that these have to be contiguous. Each node's reference field connects to the next node and creates logical sequence. Logically, they are in a sequenced manner, not physically. Physically, these are structured nodes in the heap, right? So in heap, structured nodes are there. Structured. Sorry, scattered, not structured, scattered. Not linear, but logically, these are like connected with that connection. So logically, these are, you can say, in a sequence, right? Now why we need pointer, I guess you know this thing, why you have to store pointer with that data to go to the next element. If you don't store this, how you will get to know that where is the next node? Because these are not contiguous, these are scattered. So that's why we have to store the address or the pointer. So to somewhat you can say that some overhead of drawback of linked list is more memory is required, because we are storing data as well as the pointer to the next node. So more memory is to be required, not just the data. So, and generally in 64-bit machine, a pointer, a reference in Java needs 8 bytes generally. And we know that whatever data type you store here, whether you are storing int, float, whatever data you store, according to that, the memory is to be calculated plus 8 byte for that reference. So, extra memory would be required. So, memory overhead is there, right? Okay. Now, memory representation is clear to you for this. Now, some key characteristics of linked list are, we have discussed everything. These are non-contiguous. Fine. Nodes can be stored anywhere in the memory. Sequential access. No indexing is there. No index you have in linked list like 0, 1, 2, 3. No. So you cannot directly access like we have in arrays. You cannot directly access any data. You have to go sequentially. So generally we write something like this. We represent the linked list something like this. So this is my linked list. I'm having here the data 3. This is having next. So suppose 10, next 15, next is, sorry, this is next. And we are having here suppose 20. Here I'm having at last null. And here I'm having a head pointer which is pointing to this. And here I am having a tail pointer which is pointing to this. These head and tail are reference, you can say, objects, reference variables. These are stored in stack containing the address of these. Suppose address is, suppose 1000. I'm just assuming this thing because I know that address is some hexadecimal value and all. So this head will have 1000. Suppose address of this is 2000. So this will contain 2000. Address of this is suppose 2050. So here we have 2050. Here we have suppose 1050. So 1050. Next is also having the address of the next node. Tail is having address 1050. Something like this we can visualize a linked list. So no direct access is there, no indexing is there. If you want to access 15, you have to go through first because we know head only, head and tail. So we have to go through head. First access this, then this only. So must traverse from head to access the specific elements, no direct access. So traversing or accessing any element here take order of n. But there in array it takes order of 1 and in array list. Dynamic sizing, okay, grow, it will grow and shrink as needed during run. I want to add another node, simply create a new node anywhere you can add. At the beginning, at any position, at the end. No shifting is required. Suppose I want to add here at the starting of this linked list. So first create a node. How to create a node? I'll show you, don't worry. So create a node. Suppose here I have 25 and I want to insert this here. How to insert? Just think. Don't try to think the logic. Simple steps. What is a linked list? So what you need? So definitely if you want to insert it here, so this would be the head. Yes. So you have to update this head here. But directly at first, if you update this head, this suppose address is 3000. Now here I'm having 3000. So this link is not there. Now we are lost. This is head, but this is not pointing to anybody. Here we are still having null. So we lost the reference to this list. So it's not like that we can directly update this head. No, you have to think for that. First, now we are having this 2000. So 2000 should be here because this should be the first element. So this should link here. So I want this, so not 2000, I want this 1000 here. So where you get this address? In head. So first you have to access this, then assign here 1000, sorry, 1000. So it will point to this. Now I can change, I will change to this. So now it is having 3000. That's it. So this is how we can insert. Do we need any shifting kind of thing? No. If you want to insert here, between these two, what do you need? Suppose I want to insert here 100. Address of this is suppose 5000. What you need if you think logically, not in general, like not in coding terms, simple by looking at this diagram, this visual. So you have to do something like this. This will link to this and this will point to this. And you have to break this link. Simple. Yes. So we can simply do this thing. At first we are having here null. So what? You have to update this. This 2050, this address should be here. And this address should be here. So how you will do this? Practically, we will see this thing. But for now, don't think about coding. Think about this itself. What you need. 2 steps you need. That's it. Right? Deletion is also same. You can delete from here. Just update this node. You can delete from here. Just update these addresses. That's it. No shifting is required. That's why when you need, you have some type of data and the requirement is frequently you have to insert and delete. You have to modify that data. In that case, we prefer to use linked list. So that's why we first discuss all the type of data structure so that based on the requirement you can identify which type of data structure is good to use in this scenario. It's array or array list or linked list or stack or heap or graph or what. So you have to understand some key points about all the data structures, advantages, drawbacks, characteristics. Then only you will be able to decide, okay, which data structure I have to use. Dynamic sizing, okay, fine. Node by node allocation. Memory is allocated for each node individually. Every time you create a new node, memory is to be allocated to that node, and that's it. And some linking is to be done. It's not like that in a bunch memory is allocated, like in arrays for 10 elements or for 50 elements. No. Memory, more memory is required as we are storing both data and pointer. Yeah, somewhat we can say this thing. But memory wastage is not there, like in arrays and array list we have. Because we are reserving like extra memory. It is not the case here. Whenever we need, we create a new node. For that only memory is to be reserved. So no memory wastage is there in linked list. So basically you have the idea. Types. Now types of linked list. Singly, doubly, circular and circular doubly linked list. So whatever diagram we have seen in the previous slide, that was singly linked list. Singly means you can go from here to here. So this. I can go from here to here. That's it. Head is pointing to this, and we are having here tail. Singly linked list or one direction linked list. This node knows the address of next node, but this node doesn't know the address of previous node, right? Only the address of next node, only the address of next node. That's it. So you can traverse in one direction. That's it. So this is singly linked list. What is doubly linked list? Doubly linked list, each node points to both next and previous node. So this node contains stores address of next node as well as address of previous node. So here we are having something like this. We can just update this. Here we are having 10 and here we are having 13. So this is having pointing address to this node as well as to next node, something like this. Two pointers are there, previous and next. More memory is required. But yeah, it is, we can traverse the list in forward as well as backward direction. So there are advantages of using this list. In Java, basically in collection framework, you get implementation of linked list as doubly linked list. We will see this thing also, right? And in detail, we will see one by one. Don't worry. It's just a brief intro of these linked list. Circular linked list. So this is what? Singly circular linked list. So circular means this is a single linked list, but the last node do not contain null. This contain address of this node, first node. So it's circular, something like this. No? Circle. Got it? Now, circular doubly circular linked list. So here in this case, doubly and circular. So last node contain address of this and first node contain address of this. So it's like doubly circular, right? Okay, you have, I think you got some idea about these types of linked list. Now, let's discuss more about singly linked list. Okay, fine. Head node, starting point of the list contains the first data element and the next pointer, fine. Internal nodes are there, each contains data and reference to the next node, fine. Last node contains data and the null reference indicating end of the list, right? But the thing is, now how to create a node in Java? This thing is important. Let me show you. So I told you this is a node basically having data and next. Next is a pointer or you can say a reference to next element. So it basically contains not data, address or reference to the next node. This is containing the actual data. So this is basically a node. How to create a node? Now if I want to store simple, like in array, I want to store integer arrays there. So int value is there. So I can simply take data type int. For a simple variable also I can take int type if I want to store here int type. So we need the name of that variable plus the data type. Yes. But now here it's a complete node and here I'm storing this data. Suppose this is int and this is address. It's a complete package, complete node. What should be the data type of this? Int, string, or pointer or what? We don't have any pointer concept in Java basically. First of all, we have in C and C++ that thing. Can we take int and name of the node? No, because it is containing int as well as address. So what type you need? We know that there is in Java we have concept class. Class is basically we can say it's a user defined data type, right? So in a class we can have different the type and that would be a collection like I'm having int roll number and I'm having a class student. So there I can have int roll number of the student as well as string name of the student, float or double marks of the student, boolean as well. So there's how many data types we can store here, or as well as objects as well, objects of or reference variables of another class, that is composition we can have. Yes, this thing we have seen. And then if we create like object of this student s1, so this is same like int a, variable name is a, type is int, name of the variable is s1, type is student. So this can store this much, int also, string also, float also, boolean also. This is kind of user defined data type. So this thing we need here, because here we need our own data type, user defined data type. So we can say this is a variable of type student. Here I have my own type student. So same we require here. So we can create here a class, and the name we can give the class is its node. So class and node. Here I'm having int data, plus I'm having, suppose the name I'm taking next, the pointer name is next, or reference variable name is next, any name you can take. Next, it's more descriptive, like reference to next node. But what is the type of this? Now this is one more issue. What do you think? What should be the type? This contains address of next nodes. This is my next node. Address of next node. Suppose 1000 is the address, so it contains 1000. Right? This all same. It's a node itself. Node itself. Right? So when we create a node, when you create, suppose I'm creating student class and S1. So what is happening? In stack we are having S1. In heap we are having the actual object, whatever is there for that class. In that object we are having name, address and all. So the actual data is here. S1 is pointing to this object. So basically the address of this actual object is in S1, and this S1 is of type student S1. Yes. So same, it's like a node, we can relate it. It's a node. Here we are having data and next. So we are creating a node, right? Like student S1. So same node, the type is node, and first node, second node, something like this. So here we are having same, the type should be node. It's a reference variable. Node next. So node next means store the address pointer, or the, you can say, reference of the next nodes. That's why the type is in Java, it's node. In C and C++, in C++ we take struct, and there we take pointer, but there is no pointer here. It's very simple. Node and next. I hope now you got why I'm taking here the data type node, right? Because this is a basically a reference variable to next node. And this is how we just, when we create object, so I call it, always call it student S1, suppose new student. So this S1 is a reference variable containing simply the address of the whatever actual data is there, and that's exactly we want, the address of next node. So that's why node student, node, the data type is node itself. So this is basic structure of node. Now we know the constructor mechanism, but this is basic without constructor. But yeah, we have to initialize this also. We have to give some data to create a node, right? So we can add here constructor. We know we have constructor concept to initialize the data or the objects at the time of creation itself. So public and name of the constructor will be, we know the rules, same as the class name. And then we are having here what? We are passing here int data. Suppose only data. So what we do is this dot data is equal to data, because I'm taking the same name. So this dot data, this means this, the current object, and the, you can say, the field of that object. So this data is referring to this, and this data is referring to this parameter name. And this dot, you can say, this dot next is equal to null. Whenever you create a new node, every time the data would be there something, but next is node. There is no next node. We assume that. So this is the complete thing you can write. Or you can have more constructor as well. It's like public node in data, as well as you want to give the address of next element, some node, not null. So you can assign that also. It's up to you. But at first we will take this thing only. So this is basic how we are going to create a node. Create a node. Class, node, two fields are there, data plus pointer, you can say, sorry, reference to next node. So type is node. This is constructor to initialize this object with the data. So you can simply create a node whenever, how you can write that thing. I hope you know this thing. If you have a class, because it's a simple class, it's nothing, it's a simple class. So we write here simple. When you have to create a node, and the node name, suppose I'm taking node 1. is equal to same new node, and I'm just passing here 15. So a new node would be created in heap memory with 15 actual data, and here null, something like this, right? This is the thing. This node 1 is a reference variable, node 1. This is having address of this. This is the actual object, right? You got it? Now same we can have a head reference variable or head pointer, which would be of type obviously this node, because head is also containing address of that particular node. So again, if you want to create head, so we can have node head. Simple. So one head would be there, head, and we can simply say something like this: head is equal to node 1. So this head will also have this. So we have head also. So basically the first would be considered as head node. We will see practically this thing, how to insert, how to traverse and all. Don't worry what is head and all. But at the basic, how to create a node and why? Because we are using this thing. We are using this thing. Without this, we cannot do anything, because we have to create node. So you can say, understand this thing. This is the base of this series of linked list, all the lectures. If you get this thing, you can easily move on. This is how we create a node. Suppose this is my list. So some operations, general operations, what perform in this list is insertion, deletion, and traversal. Searching is there, and few more operations are there, but main are traversal, insertion, deletion. These things, and searching also you'll see. Now, how to traverse this list. Traverse means visiting each and every node once, and we can say for maybe for printing or for doing some modification in the list. So you have to traverse, you have to visit each and every node once. So this is traversing. So this is basically for single linked list. Single linked list we can traverse only forward direction, because this is only this direction itself containing node of next element, right? So how basically you can traverse? We know we have head pointer. So one thing while traversing, although the code and all we'll see in next video what are the operation we can perform, but just theory I'm just telling you to somewhat just give you some important point here about traversal. So if you think that I'm having head, so in my this pointer, this is suppose head, I'm having suppose 1000, because the address of this is 1000, address of this is 2000. So same we are having here this. So it's not like that I have head. Okay, fine. Now just move the head, print this. How to access this? I guess you can simply write down this thing. Head dot data will give you 3. Head dot next will give you 2000, because we are having here class node data and next. The name is data and next. So this is how we can access. Like head dot data will give you the data part, and this head dot next will give you this. This is how we can access. So you see that first we will access this, then we will move head to this, then we access the data, then move head, then access this data, move head, access this data. No, this is not at all a good approach. We cannot move head. Just remember this thing. This is very important. We cannot change the structure of this list. Head is always pointing to this. Suppose if you have moved this head to this, so basically there is no connection for this. You cannot move back to this element. You lost it, because there is no previous pointer. So it's always, you can say, you have to remember that you cannot move this head. Head should always point to this. You cannot temper this head. Very first thing. So now how to traverse? Very simple. Take another variable. Another, you can say, this uh, reference variable or object of node. Just create node temp, and simply say temp is equal to head. Assign the value. So here also we are having 1000, and the temp is also pointing to this. Now very simple. Now move temp till you reach to null. That's it. And how to print? Rather than head dot data, here we will access temp dot data. Just print that. And if you move to temp, then temp is equal to, we can simply move temp of next. So after printing data, temp of next, just assign that thing to temp. So this will assign temp to next, 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 till temp is not equal to null. That's it. Once temp, this temp, in this temp, we got null value. Stop it. This is how we traverse. But one thing, we'll see this thing practically, don't worry. But one thing I just want to tell you, do not move this head in any case. To do the some kind of operations, modification, traversing and all, take another variable, another reference object, temp or any name you can take. Just for temporary descriptive name we generally take. So we generally take temp. Otherwise ABC or any name you can take. So we take temp, right? Fine. I hope you got this. Insertion to somewhat I have just discussed, right? Traversing, we have discussed now. Deletion, it's very simple. If you want to delete this data, so you have to just update this. Here, this should link to this. So change the address of this, right? So now it will contain, suppose this is 3000. So here I'm having 3000. So now there is no link between these two. So this will directly go to this. So we can bypass this. Although we haven't removed, we can bypass this. There are 2 to 3 ways to delete. That also we'll see. But basic is this. From first, from any position you can take, from any value, delete by value also there. Delete from beginning, delete from end, delete from any specific position, or delete by value. Suppose I want to delete 17 specific value. I want to delete 20. So you have to first go till 20 and then delete. You have to go till 17, then delete. So you'll see this thing also, don't worry. So basic idea of linked list is clear to you. How to create a node, what is a node, this is also clear to you, I guess. Right? Now what are few applications of linked list where these are used? So a very good example of using linked list is what uh, you have stack and queues. So these are you can say logical data structures. So to implement stack and queues, we use either arrays or linked list. So very first thing, in implementation of stack and queue data structure, we use linked list. Got it? In graphs also we use linked list, right? That also we'll see in graphs. Next, in browser, this is very good example. See, once you open the browser and like any website or anything you can take, Google or suppose jennyslectures.com. You click there, suppose here jennyslectures.com. You click on website and there are some more options, like you click on the course DSA with Java. You again click, you enroll and something like this. So now you can click back and you will be redirected backward. Or if you click on forward, that this arrow, you will be forwarded to the next page. Backward, you will be redirected to the previous page. So this is basically kind of doubly linked list. Address of reference to next and as well as reference to previous. So this is one like very great example of using doubly linked list in browsers. And a few many more examples are there, but these are few you can say very common examples, right? And one more in text editor for undo and redo, right? Because obviously maybe stack is used, but stack is implemented with the help of linked list under the thing is linked list itself. So there also we do redo, undo kind of thing. So there also linked list is useful. So there are so many applications of linked list, real world applications, right? Now last node. So we have seen how to create a node. You have to define this node class. Then we have data field. Then we have this reference to the next node. Then this is a constructor, right? Fine. Now linked list operations in Java: insertion, traversal, deletion, modification, search. There are so many operations. Now insertion implementation: 3 insertion type: beginning, end, and middle position. So beginning and end, it's take order of 1, but in middle it take order of n. Yes, in middle, because obviously you have to go till middle. So how to go there? We only have head, so you have to traverse. So in worst case, it's order of n, linear time for middle position we take it, right? Now these are some LinkedIn, sorry, not LinkedIn, linked list time complexities. To access in singly linked list, we take order of the time required is order of n because there is no direct access. Only sequential access is possible. But in arrays, it's order of 1. We have indexes and we can directly access. Insert at beginning, order of 1. Insert at beginning in arrays, shifting is required, order of n. Insert at end, order of, okay, insert at end here we can take here, I'll just show you. Order of n, order of 1. See, insert at end. So if you have tail pointer, it's order of 1 you take. But if you don't have any tail pointer, you have only head, so you have to traverse till the end and then you can insert. So order of n. In arrays, it's order of 1 at the end because we can directly access. But if there is no, the array is full, so resizing is to be required. So for that, a new array is to be created, all the arrays to be copied into the next array and something like this. So in that case, it will take order of n. Insert at middle, n, n. Delete at beginning, order of 1, but order of 1 shifting is required. Order of n, sorry, in arrays. Delete at the end. If you do not, if you have tail, then also while you're deleting from the end, you require order of n because you have to track the previous element also. The second last, not the last, but the previous to the last. Because the previous, this element, the last element you have to delete. So this is suppose the last element. Here we have null. I want to delete this. So I have to put here null. So I have access to this element. So I have to traverse till here. So that's why it will add order of n. In this case, it's order of 1. Searching order of n, same order of n. We will see all the operations insert, delete, and there also I will show you the time complexity. Don't worry. Right. So that's it about the introduction of linked list. In the next lecture, now we will see what are operations, specifically how to insert and traverse a singly linked list. And that's it for this lecture. I will see you in the next lecture. Till then, bye bye. Take care.